Hey guys, welcome to your first lecture of your last unit. How crazy is that? So we're going to be talking about gases. Now, I will go ahead and tell you that I did it in a little bit of a different order when this was recorded last semester. So I'm going to talk about gases being kind of our last topic, like last but not least, when it's really the first thing we're talking about, so don't get thrown off by that. I am starting with gases. So we're going to talk about gases, their behavior, and the gas laws. And then subsequently in our next lesson, we'll talk about solids, liquids, and intermolecular forces. And I'm really sorry that I didn't used to keep my video on, so you're not going to see my face throughout this video. And I know that makes you so sad, but I think you'll make it. So last but not least, we're going to move on to gases. This is going to be kind of the bulk of this unit. So gases don't have definite volumes or definite shape. So gas is going to take up the shape, the volume of whatever container it's in. It has the highest amount of kinetic energy, so their particles are in constant random motion. They're constantly colliding with one another. And the spacing between those particles is going to be dependent completely on the temperature, the volume, or the pressure. So, for example, this first on the left, we look at high pressure versus low pressure. If we have a super high pressure, that means our particles are very close together and are making constant collisions. Versus a lower pressure, we have a lot more space between them, less collisions, less pressure. If we look at a low temperature, our particles are moving much slower, so they're going to take up less space and be closer together. Versus if we have a high temperature, we give them lots of kinetic energy, they're going to take up more space and be further apart from one another. So gas pressure, gases and pressure are kind of synonymous with one another. If you think about when we were doing Le Chatelier's principle, or any time that we've talked about the effect of pressure, we've only been talking about it if gaseous molecules are involved. So gases are our only type of phase that creates pressure. So gas pressure is created by the force exerted by gas molecules colliding with the surface of an object. So a little bit of physics for a second. Pressure is equal to force divided by area. So whatever our pressure is going to increase when our force increases, or if our area were to decrease. So the amount of pressure is dependent on those two things. So gas, the International System Unit is a Pascal. We typically more often use atmospheres or torr. In the United States, we use pounds per square inch. So there's where that kind of force per area comes in. So here are the different units for measuring pressure. I've highlighted the two at the bottom that are given to you on your reference sheet. So if ever you were given torr and needed to convert to atmospheres, your conversion is right there. So our kinetic molecular theory, it has 5 postulates, and it kind of describes the behavior of gases. So gases are composed of molecules, so particles, whatever the gas is made up of, that are in continuous random motion. And this is due to the collisions. So a gas is going one way, a particle of that gas going one way, hits another particle, now it's going another way. They're constant random motion. The molecules that compose the gas are negligibly small compared to the distance between them. So what that means is if you took an entire sample of a gas and you took the whole volume that it was taking up, that's going to be so much bigger than the individual gas molecules themselves. The pressure exerted by a gas results from collisions between the gas molecule and the container walls. Gas molecules exert no attractive or repulsive forces. So their collisions are what we call elastic. So what that means is when they're coming towards each other with an amount of kinetic energy and they hit one another, that amount of kinetic energy is conserved. And so then they start moving outward with that same amount of kinetic energy. And then the average kinetic energy of gas molecules is directly proportional to the temperature, which makes sense because temperature is a measure of the average kinetic energy. Our first gas law or kind of equation that we're going to talk about is Dalton's law of partial pressures. So the total pressure of a mixture of an ideal gas is just going to be the sum of the pressures. So it seems pretty simple. As long as the gases don't react with one another, which that's all that we'll be talking about if we're ever using Dalton's law, then you can literally just combine their pressures to equal the total pressure of the mixture of them. So nothing too complicated. The next is the ideal gas law, and this is our big one. You did learn this in Honors Chem. We also kind of went back over it way back when in Unit 1. But any gases that follow the ideal gas law are referred to as ideal gases. They are a hypothetical construct to explain all of our different gas laws, and it does really hold up for gases under conditions of low pressure and high temperature. So we'll talk about what happens when we do the opposite, when we have super high pressure or super low temperature, and when gases don't behave ideally. But monoatomic, nonpolar gases are going to behave the most like an ideal gas. So an ideal gas, they don't have attractive forces. So they follow all of our tenets of that kinetic molecular theory. Standard conditions, so STP is always going to be, this should be 0 degrees Celsius, I'm sorry, 0 degrees Celsius and 1 atmosphere, so 273 Kelvin. And if you remember, if we plug 0 degrees Celsius or 273 Kelvin and 1 atmosphere into the ideal gas law, we get a volume of 22.4 liters in 1 mole. So if we're at STP, we can use 22.4 liters in 1 mole. If we are not at STP, we always have to employ the ideal gas law to know how, what the volume is in a mole. So the ideal gas law, a lot of you refer to it as Pivnert, is relating pressure, volume, number of moles, and temperature to the ideal gas constant. Now, these are the most common units for Pivnert. So this is going to be the ideal gas constant you're almost always going to use when you are working with Pivnert. Some things to notice: if you're not in atmospheres, you're going to have to convert to atmospheres, and if you are not in Kelvin, you're going to have to convert to Kelvin. So if you remember back to honors chemistry, you talked about lots of other gas laws like Charles' law, Gay-Lussac's law, Boyle's law. We don't care about those names. What we really care about is how they show the relationship between these different properties of a gas. So if you look at the ideal gas law, and we wanted to compare two sets of conditions. So we have a gas at one condition, and then we change something about it. What we can do is we can set two versions of the ideal gas law equal to one another. So we can say that this is in condition 1, this is condition 2. So if we were solving for any part of this, so let's say we were solving for volume 2, you know that our R is always going to cancel no matter what. So essentially that leaves us with PV over NT, those are always in the first set, equals P2V2 over N2T2. Now this should start to look familiar. In honors chemistry, you were basically always given problems where the number of moles stayed consistent. So we can take that out, and that leaves us with P1V1 over T1 equals P2V2 over T2. This is the combined gas law that you were given in honors chemistry. And if we look at this, we can see how these different things are relationally to one another. So pressure and volume, so if we just isolate pressure and volume, we see that they are inversely proportional. So as one goes up, the other goes down. Conceptually, that makes sense. If we increase the volume of the gas, its pressure is going to decrease, and vice versa. Now, if we want to isolate pressure and temperature, now these are directly proportional. If the temperature goes up, the pressure is going to go up, and vice versa. Now, if we want to isolate volume and temperature, they are also directly proportional. As the volume goes up, as the temperature goes up, the volume is going to go up as well, and vice versa. Our last one, it would make sense that volume and moles is directly proportional. The more moles of the gas we have, the more volume it's going to take up. So I show you this because you may be given problems where and we're going to do a couple in just a second, where you have to have a gas at one condition and convert to gas at another condition. But certain parts of it are going to remain constant. So going back to up here, we already talked about how we know R never changes because it is a constant. So we can just take that out. And then, depending on the problem, you can just remove parts that are staying constant. So if mole stays constant, take that away. If temperature stays constant, take that away. So on and so forth. So let's do some examples. So this first one. Mixtures of helium and oxygen are used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees Celsius in 1 atmosphere. And then separately, we have 12 liters of oxygen at 25 degrees and 1 atmosphere were pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees. So I'm going to kind of just tally up what we are given here. So we have 46 liters of helium at 25 degrees and 1 atmosphere. Then we have 12 liters of oxygen gas at 25 degrees and 1 atmosphere. Then what we're doing is we're combining them, and then they are going to be 5 liters and 25 degrees. And now we want to know what's the new pressures. Okay, so the first thing that we're going to have to do is we're going to individually have to see how that volume change is going to affect each of the gases separately. So I noticed that the temperature, so let me put this back up here. So PV, obviously our gas constant is removed because it's always going to be constant. And then here we see our temperature is remaining the same. So I can get rid of that. So really for this problem, I just have P1 V1 equals P2 V2. So for helium, I have 46 liters at 1 atmosphere equals, I don't know my new pressure when I have 5 liters. So I'm going to solve and I get my new pressure is 9.2 atmospheres. Now I'm going to do the same thing for oxygen. So 12 liters at 1 atmosphere equals how many at 5 liters? I do that math and I get 2.4 atmospheres. So those are the new individual pressures of the helium and the oxygen gas in the new tank of 5 liters. It makes total sense that our pressure went way up from what it was because our volume went way down. And then now the total pressure of them combined is simply adding them together. So our new total pressure in that scuba diving tank would be 11.6 atmospheres. Okay. A sample of hydrogen gas has a volume of 8.56 liters at 0 degrees and a pressure of 1.5. Calculate the moles of hydrogen molecules present in this gas. So you'll notice that nothing's changing here. We're not changing conditions, so we don't have to set them equal to each other. This time, we're simply going to use our regular Pivner, and we are solving for moles. So N equals PV over RT. I'm going to plug everything in, 1.5 atmospheres times 8.56 liters divided by, make sure you use the correct ideal gas constant. So we have to use the one that's in liters, atmospheres, mole Kelvin. And then we have to convert this to Kelvin. And when we do this math, we're going to get 0.57 moles of H2. So very simple and straightforward. Suppose we have a sample of ammonia gas with a volume of 3.5 at 1.68 atmospheres. We compress it to a volume of 1.35 at constant temperature. So this is another one where we can ignore temperature and we're just going to have P1V1 equals P2V2. So I have 3.5 liters and 1.68 atmospheres, and I'm compressing that to 1.35 liters, and my question is, what is my new pressure going to be? I'm going to do the math, and I get that my pressure in my second condition is 4.36 atmospheres. We can kind of do a common sense check here. I notice my volume went down, so my pressure should go up, and it did. So we're given a sample containing 0.35 moles of argon gas at a temperature of 13 degrees Celsius and a pressure of 568 torr, and it's heated to 56 degrees and a pressure of 897 torr. And it asks us to calculate the change in volume that occurs. So I'm going to figure out what the volume is in the first set of conditions first. So we have volume equals nRT over P. So 0.35 moles, my gas constant, times we have to change our temperature to Kelvin. And then we need to convert our pressure to atmospheres because my ideal gas constant is in atmospheres. So I have that 760 torr is equal to 1 atmosphere. So if I have 568 torr, I'm going to divide that by 760, and I get 0.747 atmospheres. So when I do that math, I'm going to get 11.0 liters. So now I'm going to figure out the volume occupied by the second set of conditions. So let me actually do a different color here. So now we have 56 degrees and 897. We didn't add any or take any argon away, so the moles are going to be the same. So 0.35 moles times my ideal gas constant times my new temperature in Kelvin divided by, I also have to convert 897 torr to atmospheres. I get 1.18. So then when I do that math, I get 8.0 liters. So my change in volume was 3 liters. All right, last gas law practice, we have a little bit of stoichiometry here, everybody's favorite. So we're producing calcium oxide by decomposing calcium carbonate. So calculate the volume of carbon dioxide produced from the decomposition of 152 grams of calcium carbonate. So the first thing I'm going to do is I'm going to make sure I have a balanced chemical reaction. And I do have a balanced reaction, so I don't need any coefficients. So I know that I'm starting with 152 grams of calcium carbonate, but it wants to know the volume of carbon dioxide. And I don't know my amount of carbon dioxide, so I'm going to have to start with grams of calcium carbonate and convert that to moles of calcium carbonate. And then our mole ratio is 1 to 1. So I have 34 point, whoops, I'm sorry, 1.52 moles. Okay, so now I have to figure out the volume of CO2. And this is actually even easier because it's at STP, I just realized. So we could plug this into the ideal gas law if we weren't at STP. And we get 34.07 liters. Or, since we are at STP, we actually wouldn't have had to use the ideal gas law. And we could have just said that 1 mole is 22.4 liters, and you would still get 34.07. So moving on from gas laws, it's important to understand that if we have a sample of gas, not every single particle or gas molecule is going to be moving at the exact same speed. They're going to be moving at varying speeds. However, the distribution of their speeds and their average, when they're all taken into account, will remain the same at the same temperature. And so the way we graph these distributions is called a Maxwell-Boltzmann distribution. And so you've got to pay attention to kind of how these graphs work. So a normal bell curve is something that we have seen before, but sometimes we don't really pay attention to how to read them. So what a normal bell curve is showing is like what on this side is going to be something like percent or fraction or number. And then down here, it's going to be some description. So maybe this could be varying grades. So what a bell curve is showing is that this, like all of the distribution of the amount of people with those grades, there's the fewest with A, more with B, a lot with a C, some with a D, and very few with a, well, I guess we don't really have an E. But a skewed bell curve would mean, okay, now if we look at these, we have way more people who have an A and very, very few that have like C, D's, and E's. So we have to look at the graph that way. So here's an example of a Maxwell-Boltzmann distribution for nitrogen. Okay, and so you'll notice that all of these are nitrogen. Down here, it's showing our velocity. So for gases, that's always basically going to be our x-axis, and y is going to be fraction of molecules. For this one, we have the same substance every time, but we're changing the temperature. And what you'll notice is that the curve is flattening as we increase the temperature. So a lot of AP chemistry teachers have been joking when the whole flatten the curve came out, because we were all saying that, oh, these are just Maxwell-Boltzmann distributions. But anyways, so you'll see when we're at 100 Kelvin, that's the lowest temperature on the graph, the majority of our gas molecules are at around 250 meters per second. That doesn't mean that there's none below or above that speed, but the majority is here. When we compare that to 1,000 Kelvin, now the majority are closer to like 550, or sorry, 750 meters per second. So we see how that curve flattened, and what that flattening of the curve means is that the majority are now at a higher velocity than the majority of the particles were at a lower temperature. So now we're looking, that first graph was showing how when we increase temperature, we increase velocity. And the reason that happens is because we are increasing the kinetic energy that these particles have. So if they have more energy, they can travel faster. Another relationship we can look at is mass and velocity. And this comes from the equation of kinetic energy is equal to 1/2 mass times velocity squared. So you are never going to have to plug numbers in for this, but you need to understand the relationship. So if we have gases at the same temperature, all the gases are going to have the same kinetic energy. That's really important to understand. So in this graph, it doesn't show me what temperature, but like let's say that this is at 273 Kelvin. All of these gases are at the exact same temperature. So all of them have the same kinetic energy. But what's going to change is their mass. As we get heavier, we move much slower. So that's why the curve for xenon shows the majority of particles moving very slow, while the curve for helium shows the majority of molecules moving much faster. So a big takeaway point here is that increased mass means decreased velocity or speed. It does not mean they have a different kinetic energy. They're just moving slower because they're bigger. Okay, so we said earlier that we are going to talk about when gases don't act ideal. And so the ideal gas law is going to fail when we're at high pressures and low temperatures. Now, why would that be? When we're at low temperatures, our particles are going to move very slow. And that's going to allow for more attractions to one another. So those intermolecular forces can be a little bit more at play. If we're at high pressure, if you remember way back when we were talking about gases on the first slide, if we're at high pressures, the space between the gas particles is going to be a lot less because they're colliding so much more. That's what gives the high pressure. And so the volume is no longer going to be so negligible. So there's something called the van der Waals equation that corrects for the behavior of real gases. So ideal gas law, we just have PV equals nRT. The van der Waals equation adds two parts to account for these two things that are no longer true. You will never, ever, ever have to plug numbers into the van der Waals equation to calculate things. What you do need to understand is the two things that the van der Waals equation corrects for. So it corrects the pressure by taking into account the attractions, and it corrects the volume for taking into account that the gas particles are no longer negligible in volume. So what you would need to be able to tell someone, to relay, is that ideal gases, real gases, vary from ideal gases due to two things. The attractions are no longer negligible and the volume is no longer negligible.